folks, good morning. I just want to remind you that we do have an exam coming up. It's on your syllabus. It should be on the back of your book as well, but we're sitting right here, so we have pronouns in here, so we have an exam on Friday. That's the Friday right before Mardi Gras. And that exam will definitely cover chapters 0 and 1. We might even get a little bit into 0.5. But 0.5 is really just a rehash of chapter 0, but instead of gravitational fields, we're looking at electric fields. So may or may not get to that. We'll see sort of how things go in the next couple days. But I suspect that we will get partway into it. All right, so in the meantime, you can be looking at the homework. Again, the homework to sort of help to prepare for the test, looking over those concept tests. I'll post the chapter 0. Let me make a note of myself. I'm going to post that chapter 0 concept test that we did. And look at those old exams. So go back on the website and start looking over some of those old exams. In fact, I go ahead and print out the exam ones over several semesters. And every day, just work one problem, maybe two. Go through it, spend 20 minutes a day on it, and then you should be in a pretty good place for the exam coming up next week. Okay? How has your first week been? We're sort of 1 week in now. Been okay for classes for you? I know it feels like we've been in school for like a month, but we're really just 1 week in. Yeah? All right. I heard several of you comment about this class being early. It is early. I mean, it's always been early, but it's good preparation, because when y'all go out and get jobs doing whatever, some of you might have to go in even earlier than 7:30, so it's good practice for you, and it's a good time in the morning when your head is sort of clear to think about other things. Just get a good night's sleep. Don't go out partying every night or whatever it is that y'all do. Okay, let's see. Somebody tell me where we left off on the concept test. What number were we on? Okay, so we haven't gotten to the Coulomb slide yet. Okay, thank you. Okay, so we're going to do Coulomb's law. This is basically exactly the same as what we did with Newton's universal law of gravitation. Like I said, that's why we did that when we did that chapter 0, because there's a lot of parallels between electric forces and gravitational forces and the way that we treat them. Coulomb's law describes the force between two charges. Remember, the gravitational force was given by m over r squared. Well, in a very similar way, Coulomb's law gives the electric force, which is going to be k, which is a constant called Coulomb's constant. I'll give you that in just a second. Times charge 1 times charge 2 divided by the distance between them. And we're going to take actually the absolute value of these charges, because remember, a charge can be either positive or negative. We'll take the absolute value of those charges. We'll never include the signs. So these are our two charges. This is our distance r between them. And Coulomb's constant, which is k, that's equal to 9 times 10 to the 9th. See, that is in Newton meters squared per Coulomb squared. Just looking at the units of this equation, it has to be in that. Q is in units of coulombs. And R, of course, is in our SI unit of meters. We're going to often be dealing with small units because often these charges are very small. So let me just remind you of some of your metric prefixes. You should know all of your metric prefixes, of course, from nano all the way up to giga by orders of 3, except of course for centi, which falls out of that. So giga is, or nano is 10 to the minus 9, micro is 10 to the minus 6. That's one that we'll use commonly. Nano is 10 to the minus 9. Going on up, milli is 10 to the minus 3, centi is 10 to the minus 2, kilo is 10 to the 3rd, mega is 10 to the 6th, and giga is 10 to the 9th. So you need to know all those, but particularly these. If you've forgotten those since last semester, that's okay, but just review them a little bit. Make sure that you know your metric prefixes. Also a common one that we'll use is centi. just 10 to the minus 2, like a centimeter. Okay, so Coulomb's law is similar, as I said, in form and action. What I mean by that is it's similar in form in that it is a force proportional to 1 over r squared, and then also proportional to q. So it's inversely proportional to q, it's directly proportional to q, inversely proportional to r squared. And in action, meaning that if r increases, f decreases by a factor of that squared, that distance squared. So in form and action, to Newton's universal law of gravitation. And we'll see in this chapter and in the next chapter, as I said, that a lot of what we did with the superposition of vectors, with Gauss's law will also apply, with fields, with potential energy and potential. All that's going to apply to electric charges. So we'll begin to see a lot of that in the same way. Newton's third law also applies. Remember, Newton's third law says that if any time I have a force, there has to be, right, a what? Right, another force is exactly equal in magnitude but opposite in direction. So you can never have a force that's all by itself. It always has some companion in that way. And that's true for Coulomb's law as well. It's a little bit different from the gravitational forces, because with gravitational forces, if I had two masses, they were always attractive, so their forces were always in that direction. That's not true for electric forces, because opposite charges will attract, like charges will repel. So we need to remember those basic properties of charge, that opposite charges will attract and like charges will repel. So here I have a force on particle 1 due to particle 2. I'm going to have an equal and opposite force on particle 2 due to particle 1. So the magnitude of F21 will equal to the magnitude of F12. That's also true if they're opposite charges, but now they're going to be in this direction. This is F12, this is F21. Also notice that when we wrote Coulomb's law, K, Q1, Q2 over R squared, in the actual form of Coulomb's law, you need absolute value signs here. I won't write those absolute value signs, but we'll just always remember that Q1 and Q2, these are the magnitudes of those charges. The reason we don't include the signs of the charges, the signs really only affect the direction of the force, and we'll always account for the direction of the force whenever we're dealing with these by drawing the vectors. And then that's how those signs come in. So whenever we're using Coulomb's law, we'll just take Q1 and Q2 to have no sign at all, to be positive, even though it might not be that case. Okay? So superposition principle, we're going to do one more vector problem. I think actually we might have one more after this. So, but you're going to have a 2D vector problem on the test. So if you haven't gotten it yet, then please get it in the next couple of examples or on the homework. If you have, then just practice and that's fine. So when you have two or more charges, you can determine the force on one of the charges just by adding the vector forces. Oh yeah, okay, so for example, let's do this example. I want to know the net force on Q3. This is Q1, Q2, this is positive, this is negative, and so I want to know what is the net force on Q3. I can first draw the force on Q3 due to Q1. To the left or right? The force on Q3 due to Q1. Q3 is positive. Is that force on this charge due to this charge going to be to the left or to the right? It's going to be to the right, right, because it's repulsive. I have two positive charges, and so it's going to be in that direction. That is going to be F31. All right, and then I also have F12. or excuse me, F32, which is going to be in this direction. So that's F32. Now I want to know what is the net force. The net force, remember, is just the sum of the forces, the vector sum. In this case, that's going to be F31 minus F32. So our first job will be just to calculate what F31 and F32 are. F31 is KQQ over R squared. That's K Q3 Q1 over R31 squared. 9 times 10 to the 9th. Remember, I told y'all about the E. Yeah, Ainsley?
You use the minus there because you're going to the left, correct?
Right. So in a right-handed coordinate system, to the left is always negative. Thank you. All right. So remember, with your calculator, use that exponent key. It'll make your life a lot easier in this class and others. Q3 is 4 coulombs. Q1 is 2 coulombs divided by the distance squared. That's 3 meters squared. So that cancels with that, and I'm left with 8 times 10 to the 9th. I just used some big charges just to make the numbers easy to deal with. A coulomb is a whole lot of charge. So notice if I have these huge charges next to one another, they feel a huge force, 8 giganewtons of force. That's a big old force. All right. F32 is 9 times 10 to the 9th times 4 times 1 divided by the distance between 3 and 2. That's going to be 2 meters squared. This will cancel with this and gives me just 9 times 10 to the 9th. So our net force is going to be F31, 8 times 10 to the 9th, minus 9 times 10 to the 9th. That's 8 giganewtons minus 9 giganewtons, which is 1 giganewton. So 1 times 10 to the 9th newtons. All right, that's a 1D problem. You'll see in your multiple choice part of the exam next week on Friday, you'll see some questions that are one-dimensional in nature, but not numerical. So we'll see some questions later in the concept test where we're asking, well, if I had this charge here and this charge here, what is the force that's at play there? And, well, we'll see some examples of that. But on your test, you're going to, in the free response section, you'll have, that should be negative. You'll have, was that your question? Yeah. I could see the question on your face before you even asked it. Ainsley?
All right.
Okay. What was I saying? On the free response section, you'll have a 2D force vector problem. It'll either be gravitational, electric forces, or electric fields, which we'll see next time. So make sure you can do that. All right, so let's do a 2D problem. I'm going to sort of go through this quickly. We've done this once before. I think y'all know how to do this. But again, if you don't, use this time as a time to sort of see it again. If you do, just use it for practice, knowing that you'll have to do it on the exam without any help or whatever. So here I want to know the force on Q3. First job to do is to write out the vectors on Q3, draw them, ask yourself what are the directions of the forces due to this particle and this particle. Then we need to ask ourselves some question about the direction of those forces. And then we'll need to calculate the magnitude of the forces. Then we'll need to find the x and y components of one of the forces because it's going to be off-axis. And then we'll need to add those x and y components. And then we need to find the resultant magnitude of the magnitude and direction of the resultant vector. So several steps we have to go through. Let's start. So first, I'm going to draw my coordinate axis on the force on the charge that I'm looking at. I'm going to draw the force vectors. I have Q1 Q1 and Q3 are both positive. So my force vector will be up and like that. That's going to be F31. And then my force vector F32 will look like that. I've asked the question, what is the are they opposite or like charges? Are they going to attract or repel? They repel in this case, they attract in this case. Next thing I want to do is I want to find out what this angle is. Take just a minute and try to determine what is that angle. Do notice that this is a special triangle that we're dealing with. It's a 3, 4, 5 triangle. You might by now just know the angles for that triangle. You should certainly know the hypotenuse. All right, so what is this angle? I'll call it theta. What is that angle theta? Just take a moment. You need to draw a picture of your triangle on the figure. You can hopefully begin to see that angle. All right, hopefully you recognize that this angle has what relationship to this angle? How are those two angles the same or different? They're exactly the same. Anytime I have two lines that cross like this, these two alternate angles, I think, are the same angles. So whatever this angle is right here is going to be the same as the angle that I want. On a 3, 4, 5 triangle, the angles are 37 and 53. Which one is this one? It's 37 because it's opposite the smaller side. So on a 3, 4, 5 triangle, I have 37 degrees and 53 degrees. I know this one's 37 because it's opposite the smaller side, so it has to be the smaller angle. So this angle is 37 degrees. The next thing I want to do is find the magnitudes of these forces. So I want to find what is the magnitude of F31 and F32. I've already done that on the previous problem. I'm just going to give you the answers for F31 and F32. F31 is 1.08 times 10 to the minus 9. And F32 is 1.13 times 10 to the minus 9. One thing that I have done here, I've mentioned this. This is a special triangle. It's a 3, 4, what type of triangle? 5. That just means the hypotenuse is 5. I like to use special triangles so that you're not dealing with Pythagorean theorem a lot. So if you know that triangle, that'll help you. The hypotenuse is 5 meters. And so when I calculated F31 right here, I had to use that fact because that's the distance between the charges. If you forget the special triangle 3, 4, 5, to find the hypotenuse, of course, you say the square root of 3 squared plus 4 squared. That's the square root of 25, which is 5. Okay? You with me, folks? This is just extra practice for you? Or maybe it's sort of welding these things together in your mind. Okay, so now I have the magnitudes of those vectors. What's my next step in finding the sum of F31 and F32?
Get the x and y component of F31.
That's right. I need to find the x and y components of any vector that's not on axis, and then I'll add up all the x and y components, and then I'll be almost there. I can find the resultant vector. So I find F31x is 1.08 times 10 to the minus 9 times cosine of 37. So Katoa, cosine is adjacent over hypotenuse. Ainsley?
Are they supposed to be positive? to the exponents? So
No, they should be negative.
they should be
Yeah, I didn't do the Coulomb's law, but when you go through, because you have two charges that are nanocoulombs, that was your problem.
okay.
The nanocoulombs is 10 to the minus 9. If you don't include the nano, it will come out positive. Is that clear?
Yeah, I didn't understand that and was.
Yeah, it is nano. Okay, so F31X, if I do that, it comes out to be, well, something, I don't know what it is, doesn't matter. And then F31Y is 1.08 times 10 to the minus 9 sine of 37. Let me just go back and address that question again. So Ainsley asked, should this be positive or negative? K QQ over R squared. If you don't include the metric prefix, which is nanocoulomb, then it comes out positive. And so, for example, here, if this is Q1, Q3, Q1 should be 3 times 10 to the minus 9, and Q3 should be 1 times 10 to the minus 9. All right. And then you can cancel out some of your minus 9s with the K, because it has a times 10 to the positive. Okay, people? All right. All right, so now I can redraw my vectors here. I have F31Y I have F32 and I have F31X. Now I can combine these two vectors because they're both on the x-axis. The sum of the forces on the x-axis will be F31X minus F32. And that turns out to be negative 2.67 times 10 to the minus 10. The sum of the forces on the y is just F31y. That is 6.5 times 10 to the minus 10. That is this value right here. So now I have the x and the y components. The y component of my vector is right here. The x component is in that direction. It came out negative here. And then I find the magnitude in the direction. To find the magnitude, I say the square root of 2.67 times 10 to the minus 10 plus 6.5 and that gives me my magnitude, which is going to be 7 times 10 to the minus 10. And then I can find my angle. I'll call it phi, or I use theta. My resultant vector is going to be in this direction, so I'll be finding this angle phi, tan of Fy over Fx, opposite over adjacent, and that works out to be 67 degrees. But I have to give a qualifier above the negative x-axis. So that's the final answer. That is the net force on that particle, and that is the direction, 67 degrees. All right, people. We'll see one more 2D force problem. We won't. I think it's a little bit simpler than this one, but we'll see one more before we see it on the test. And if you're not getting it, it's on the homework too. So a couple of different examples on the homework. Let's do a few quicker questions. what is the magnitude of the force F2? Again, these are in the back of your book in the appendix if you want to follow along there and mark the correct answers, and I'll post them online as well. What is the magnitude of the force F2? All right, just a few more seconds. I'll stop at, say, 53. Just guess if you don't know. Okay, awesome. D is the right answer. It's Newton's third law, right? That F2 has the same magnitude as F1. And what do you get? You're gonna love this one. What do you get when you cross a chicken and a mountain climber? You can't. A mountain climber is a scalar. Because cross products are vector products, right? Yeah. I'll be here all week. Okay, if we increase one charge to 4q, what is the magnitude of F1? All right, I'll stop at 50. Stop at 50. Okay, good. C is right. Remember, on these type problems, when you have this relationship, it's always good to just write out the equation or look at it on your equation sheet. KQQ over R squared. If I increase one of the charges by a factor of 4, then I have to increase the force by a factor of 4. When the force was 4, it is now 12. It's increased by a factor of 4. The force between two charges separated by a distance d is F. If the charges are pulled apart to a distance 3d, what is the force on each charge? Feel free to ask your neighbor what they put. Oh yeah, see me after. Devin, see me afterwards. We'll talk about it. Okay. Let's see. I'll stop at 50 at 1 minute. All right. E is the right answer. If I increase R by a factor of 2, or by a factor of 3 rather, I decrease F by a factor of 9. So KQQ over R squared. If I increase this by a factor of 3, it's squared, so I get a 1/9 F. Two balls with charges plus Q and plus 4Q are fixed at a separation distance of 3R. Is it possible to place another charged ball on the line between the two charges such that the net force on Q0 will be 0? So can you take a charge and place it somewhere along this dashed line? such that the force on it will be 0, such that the force on that charge Q naught be 0? And what must be the sign of Q naught? Or does it not matter? Or no, can you never do that? I want to put a charge somewhere along this dashed line such that the force on it is 0. This is what I mean by a 1D problem, but qualitative. And there are many variations to this, but I'll show you how to think about it. All right, I'll stop at 125. Okay, yes, C is right. Let's see. So if I take a charge and I put it in the middle, say right here, and let's say that it's positive. The force due to this charge will be in this direction. It'll be repulsive. The force due to this charge will be in this direction. It'll also be repulsive. But also imagine, what if I take a charge, a negative charge. I'll put it up here, but imagine that it's on the line. The force due to the minus 4Q will be attractive. The force due to the plus 4Q will also be attractive. All right. Where does the charge have to be in regards to this line? Does it need to be right in the middle, over here, or over here? It needs to be closer over here because it needs to get farther away from this bigger charge, and then that'll, there is a point, and you can calculate what that point is, where these two forces will cancel out. We'll see a problem like that soon, and also in the homework. Proton and electron are held a distance of 1 meter and then released. As they approach each other, what happens to the force between the proton and the electron? All right, I'll stop at 45. All right, A is the right answer. It gets bigger. As they approach each other, the force between them gets bigger because that force is 1 over r squared dependence. As r goes down, the force goes up. It gets a lot bigger. So A was the right answer. It's bigger. Which one has the larger acceleration? Think Newton's second law. Which one has the larger acceleration? Is it the proton or the electron? Right. We'll say 38. And B is the right answer. Why is B the right answer? Right, it has a lot less mass, right? The electron is like 1/10,000th the mass of the proton. The proton's a lot bigger, right? The electron is like a 10 to the minus 31, and the proton is like 10 to the minus 27 kilograms. So the proton is a lot more massive than the electron. And so the electron will have 1,000 times the acceleration, or no, 10,000 times, did I say 1,000? 10,000 times the mass, or 1/10,000th the mass of the proton. Okay, they're let go, a distance of 1 meter, and let go. Where do they meet? The middle, closer to the electron, or closer to the proton? All right, I'll stop at 35. 35. Awesome, C is right. Since the electron has more get up and go, it gets over closer to the proton more quickly. It accelerates more readily. Which of these best represents the direction of the net force? On the plus Q charge, let me move that so you can see it. Let your numbers be letters. 1, 2, 3, 4, 5 is A, B, C, D, E. All right, I'll stop at 43. 43. That's right. Likely you'll have something like this on the test, some sort of qualitative vector analysis thing where you're looking at vectors and asking, what is the resultant vector? The way you do this is you just draw the component vectors from each individual force, and then you ask yourself, what would be the sum of those vectors? So, for example, I can draw the force vector due to this one. It's going to be in this direction, and we'll say it has that length. And then I can draw the force vector due to this vector. It's going to have a length that's twice the length of the first vector that you drew. It's twice the length because this has twice the charge of this charge. And they're equidistant from the other charge. So those are my two vectors. If I add those up, I don't get this one, I don't get this one. If they were equal, I would get vector 3, but since the y component is bigger, I get vector 2. So B was the right answer. And we'll get to electric fields next time. Let's do a couple more. I think I have a couple more clicker questions here, actually, and a quick test for you to try on your own. This is a similar question, but a little bit different. Which of these represents the net force on the rightmost charge? So which of these vectors represents the force on this charge? A, B, C, D, or E? All right, we'll stop at 55. Say. Just guess if you don't know. I think that's right. Let's see. So I just draw my component vectors, each one. The charge, or the force here is in this direction. The force due to this charge is going to be in this direction. I draw it smaller for two reasons. One, this charge is half the charge of this one, so it's going to feel a smaller force just because it's a smaller charge. But then also, the distance is the hypotenuse, and the hypotenuse is greater than any one of the sides. So this charge is going to contribute to bigger force by at least a factor of 2, but actually a little bit more than a factor of 2. It has twice the charge, and it's closer, so probably more like a factor of 3. So I probably actually underestimated the difference between these. And so when I add up these two vectors, one really big, one really small, my sum here will be E. Did many of you put D? D is sort of like the next best answer. No, nobody put D. Somebody put A. What is A? Okay, well, A would represent the force just due to this charge, but it doesn't take into account this charge at all. So A doesn't really jive. But D, you could rule out D as an answer just because this vector is so much smaller than this vector. So when you add up those vectors, this big vector is going to pull the resultant vector over into this quadrant because this vector is so much bigger. Alrighty. Now let's try this one. I'm going to give you all a few minutes and we'll sort of spend the last 10 minutes or so of class working through this. This one's similar to one we did, but y'all try it on your own. I have three charges here. I want to know the magnitude and direction of the force acting on this charge. And then I want to know the x and y coordinates for a fourth charge such that the net force on this charge would be 0. Similar to what we had before, it's on a 3, 4, 5 triangle. You'll need to find the magnitudes. You'll need to find the direction of one of the vectors because it's not going to be on axis. Then you'll need to find the x and y components of that off-axis vector. And then you'll also need to find the sum of the x and y components. Right back up to 14. just to give you a little, make sure that your numbers are right so far. I get F13 to be 0.00216. I get F12 to be 0.008 newtons. Do I concur with that? Yeah. And in just a second, I'll draw the X and Y components. I'll give you a little head start first. Some of you might have already finished A. I got this answer for A. I got 0.0098 newtons at 82 degrees from the negative X. So what y'all got? Any of you got A? Yeah. Not yet. Was that I hadn't gotten it yet, or was that I didn't get that? Oh, all right. That's fine. Keep going. I'm going to draw my X and Y components of F13 and F12 here. I've already done the sine and cosine bit. Concur with those numbers, somebody? This is the magnitude. Yeah, Ainsley. Oh yeah, you're right. I'm sorry. Were you asking the same thing? Yeah, you're right. Okay, I'm sorry. I just made a mistake. Sorry, I was doing it in real time too. So they asked the vector here. I had drawn it like this actually, but it should be the other direction. The magnitude is going to stay the same, but it's going to look like that. And then this vector is in this direction. So let's see, that changes, did a little bit, changes the answer too actually. Sorry about that, folks. Let's see, so the component that changes now will be this one should go in this direction, right? And right, which one is it? It's the 0.0017 should go in this direction. Thank you for catching that. That should be correct now. And now that's going to change this. It's going to be 0.0063. Okay? Does that sit better with you? Good. All right, and then I can find, that means these answers are wrong. Say the square root of 0.0063 squared plus 0.0013 squared. You get 0.0064. And then the angle is the inverse tan of that y component over that x component. 63 over 13. 78 degrees. Still above the negative x. Alrighty? Yeah, Megan? Guys, we're out of time now, so we'll come back and finish this up because there's a second part to the problem with if you are new to the class, or like if you're a transfer, just please continue to chapter class. Logan, just make sure that you sort of know where things are going here.